machine learning. So I'm the chief data scientist for a small startup called Anodot. We're based in Israel. It's a startup that does anomaly detection. I'll describe it a little bit in a few minutes. And as a startup doing machine learning, we quickly reached a point where we need to track what our algorithms are doing, and I'll describe how we do it. So a little bit about machine learning. How many people here have background in machine learning? Okay, so quite a bit. So when I did my PhD in this area, it used to be about publishing papers. You take data set, you get slightly better results than the previous guys on the data set in computer vision or text or whatever field it was. You publish your papers in ICML and NIPS. You do some theoretical work. It was very nice, but this was the only people who knew what machine learning is. But in the last few years, as we all know, there is the coming of age of machine learning, and with many, many applications that are actually working for large companies. It started with a lot of things around ads and recommendation systems in e-commerce, and we're moving into autonomic cars that have deep learning engines in them that are going to actually change the way our life completely. So machine learning is coming of age, and it's also, sexy now to be a data scientist, which is, I would say, a synonym for machine learning. The sexiest job of the 21st century, according to the Harvard Business Review. That's nice. So it's nice to be in the field that is being appreciated today. But we still have a long way to go until it actually reaches maturity. So let me talk a little bit about the practical machine learning process. When you start with a problem, you define it. You define a business problem. Either it's given to you, or you have to go and figure out what is the problem. That is the first step, and decide that machine learning can actually help solve that problem. The next step is to start collecting and preparing the data, and that is a very difficult step, but necessary one if you want to try out any algorithms. And then after you have your data, you created your features, you start training and testing your models, and you iterate a lot of times over that. You fail for 100 times, and then the 101st time you actually get some decent results. You're happy, you have good models, you believe you've found the right algorithm that will solve that business problem. Now you deploy it to production. Another step, which is not that easy. Now that you deploy it to production, you have to start tracking and monitoring it, because it's actually going to be in front of people, it's going to do something continuously, and you have to make sure it continues to do that. So that's the 5 steps of the machine learning process. And if you look at the world out there of tools and companies that are building machine learning capabilities, both internally and providing them either as an open source or as actually commercial offerings, then you see they focus a lot. First, they focused a lot on collecting and preparing the data. I mean, Hadoop is basically a new platform for collecting the data, and then on top of it, so many things that prepare the data. And you have Spark, and you have Trifecta, which is a commercial company doing data preparation and data refinement. Now you have a lot of companies coming out in the last year, both in the open source world and in the non-open source, doing automation around training and testing the models. So they're trying to democratize it so everybody can use these models without having deep knowledge of the theory behind them. TensorFlow, AWS machine learning, Azure machine learning, companies like Dato and Spark MLlib, which is an open source. And of course, once you train and test the model, you need the mechanism that will actually deploy it to production. So a lot of companies work around that. And if you look at the landscape, and this is from March 2016, it's an analysis of the landscape of machine intelligence. It's getting very, very crowded and busy. I mean, it's small, but for a reason. And actually, since March, there were at least a few others that came into this world that are not in this slide. So lots of tools, platforms, and solutions, but there's actually one area that fifth step that you don't see a lot of solutions, you don't see it being addressed by any of the either open source or commercial solution. I deployed it. I have my models in production. What happens now? How do I track and monitor them? What do I do? So this is a slide I got from Dato, which is a company doing machine learning platform. And they put in their slides, well, you deploy your models, you evaluate them, now monitor and manage them. But what are the steps for doing that? Well, they're pretty simple, actually, if you think about it. The first step, you define what are the performance metrics and expected behaviors of your model. If I deployed a recommendation engine and I tested it on a lot of training and test data, I can expect some performance out of it when it goes into production. And then I can track it over time and see whether that changed. If I'm doing classification of faces or classifications of cats and dogs and other objects, I know more or less what is my distribution of object recognition that I should expect, and if that changes, maybe my models go wrong. Or if I'm building an autonomic car and I trained it on a lot of different objects and to react to a lot of different situations, if there is a new situation that comes up, I would want to track it with metrics, detect it, and then refine the models if that is necessary. So, but how do I do that? How do I actually track and monitor all these different performance metrics for all these models that I've trained? And doing it manually is probably not an option. And why? Because it's hard. There are many models out there. If I'm deploying autonomic cars, I cannot do it manually. Well, I cannot wait till a data scientist detects that there is an issue that I didn't recognize the kangaroo in Australia because I never trained my models on detecting kangaroos, and wait for the cars to hit it before I actually go and fix these models. So it won't be an option to do it manually. So what is the solution? Well, there are a lot of solutions. I'm going to propose one today. And it's one that is kind of biased towards what our company is doing, which is anomaly detection. So, so forgive me if it's a little bit biased towards that, but it is a solution that works, and it's not only me that, that is proposing this solution out there. So a little bit about Anodot. Anodot's platform is not meant for tracking machine learning algorithms. It's really it's a business incident detection platform. We take time series signals from many different sources, from many different domains, either telcos, IoT, web services, e-commerce sites, industrial IoT. And the platform provides a lot of analytics capability and machine learning capabilities. One of them, or the major one in them, is anomaly detection. And the reason we provide that is to detect business incidents automatically without the need of dashboards or manual configurations of static threshold alerts and all the normal things that people do in their monitoring system. So some examples of business incidents, for example, this is a drop in number of visitors for one of our customers, and you can see that the drop is somewhere in the middle of towards the end of the day, but not on a weekend. And the reason it's an anomaly because there is a change in the temporal pattern that is very easy for our eyes to see, not necessarily very easy for algorithms to track and detect. This is decrease in ad conversion on Android for an ad tech company. Or my favorite one, a price glitch in an e-commerce site where they posted a gift card worth $200 for just $15. Twitter, Facebook, people got the word, started buying really quickly at that low price. Who wouldn't buy? And this happens to airlines a lot and to other e-commerce sites. And then they see an increase in the number of purchases of gift cards, which is great, but then the revenue does not increase. And the revenue is the graph below, does not really increase as expected. So that anomaly is actually represents a price glitch. If you don't detect it really quickly, you're going to lose a lot of money. So this is why we built Anodot, not for tracking machine learning. But then on the way, as a data scientist, it's very easy to understand why the same technology can be applied for another domain. So anomaly detection really helps to detect the unknowns. And this saves time and money to a lot of industries, from web services, IoT, and security. And as I mentioned, it helps to also track machine learning algorithms and close the loop by detecting unknowns that you didn't think about when you created your models. So you created a classifiers for detecting 20,000 objects. When the 20,001 object came along, you wanted to be able to detect that that happened so you can refine your models and improve them, either automatically or manually, but at least know about it. Otherwise, your models in production are going to perform very poorly. Or if you introduced a bug like this, this is a graph of classification accuracy of an algorithm, and you introduced a bug at some point in time because you deployed a tuning algorithm, and all of a sudden your accuracy drops, you want to be able to detect that as quickly as possible so you can fix it. And this is just like, as I said, coming of age of machine learning. It has to go out of the lab into the real world, and therefore it has to be monitored and tracked and fixed really quickly when it goes wrong, just like any other software. So a little bit about what is anomaly detection. So anomaly detection is an interesting field in machine learning. Let me start with an exercise and see if there is somebody quick here that can detect the anomaly in this picture. Right, there are always 2 people or 3 people that detect it really quickly. It took me 5 minutes, so don't feel bad. So this is the anomaly here, this penguin, and the reason is, if you still haven't figured out, the eyes are pointed down. So we're very good at detecting visual anomalies, but this was a simple case where the anomaly is clear. Usually, it's really an ill-posed problem. What is an anomaly? An anomaly is almost subjective. So here are 6 pictures. And you can probably, based on some definition, say that each one of them is an anomaly in some sense, right? There is only one male, one black and white picture, only one black woman, only one unknown sex woman. So every one of these is an anomaly in some sense. And it's okay, so it's ill-defined problem, but still we use it. We use it because we define some sort of definition of what is normal, and based on that, we can say what is abnormal. So we're mainly talking about anomaly detection not in images, but rather in time series signal, because we're tracking performance of things with metrics. So metrics you can plot over time. And really an anomaly detection in time series signal is an unexpected change in some temporal pattern for one or more combinations of time series signals. And these are real anomalies for various type of businesses. And you can see sometimes you have multiple series that are abnormal. You have temporal patterns that are seasonal, and you have trends that change over time. And this happens, and these are anomalies by their model's definition. So a little bit about anomaly detection methods, so we're on the same page. So the general scheme of anomaly detection, at least for time series, and again, I keep mentioning it's for time series, is you have your graph, and the bold blue line is the actual graph. And what you try to create is a model of what is the normal behavior of that graph or combination of graphs using a statistical model. And that is basically, that choice of statistical model defines what is normal. Once you have that, you devise a statistical test to determine if any of the samples are within, that are explained by the model. And visually, the statistical test is shown here using that band, that light blue band around the graph itself. So any sample that is not explained by the model, in this case goes outside the normal range, is an anomaly, and that's how you flag it as an anomaly. An anomaly can be bad, an anomaly can be good. We make no, the context of an anomaly is really in the domain that you're applying it to, but an anomaly is a change of a strong deviation from the normal pattern. So there are 2 main types of anomaly detection methods. One is online anomaly detection algorithms. These are the most commonly used, at least for time series signals, when you're applying them in real time. And in them, you actually initialize a model with some samples, small sample set. And for each new sample, you test whether it's an anomaly or not. And then you update your model. So these models continuously get updated. And these are the types of models we use at Anodot, because if you want to scale out and be correct for millions of these time series signals, then you have to be adaptive. And the world changes all the time. Some example algorithms for people who are interested. You've got simple moving averages, exponential forgetting, Holt-Winters algorithm, which is double, triple exponential, Kalman filters. A lot of these are taken from the statistics and signal processing world, and not surprisingly so, because signal processing deals with time series signals quite a lot. The other set of algorithms are batch anomaly detection algorithms. They're better for things that are more static, that don't change, or you don't need to run them in real time, and you don't need to get anomalies in real time. And also, you can afford very large batch jobs of learning. In those cases, the scheme is you collect historical samples, you segment the samples to kind of similar behaving segments. Clustering algorithms typically are what are being used. And then you cluster them to these segments using some similarity measure. And that similarity measure is what defines normalcy in a sense. And then you mark anomalies, any segments or any samples that are not very close to any large cluster. So those are the anomalies. Some sample algorithms for that. PCA, one-sided support vector machines, multimodal distributions, hidden Markov models that are used a lot in speech, but also as anomaly detectors. Some of the most commercial common ones are variations of k-means, dbScan, mean shift algorithms. And again, you use the clustering, you find the clusters, and then you find the outliers that are outside of these clusters. So I've talked about some of these algorithms. Now, let's switch to how the topic of today, how do we use anomaly detection to track machine learning algorithms? So I'm going to talk about Anodot as a use case, but you can think about it as something you can use for any other system that has machine learning. So our system in general has 5 steps to detect anomalies. In the first step, we collect all these time series signals in real time, and then we learn continuously the normal behavior models. And here actually are hidden about 12 different algorithms, plus a classification algorithm, because we have to, like I said, not the choice of model that you have will define what is normal. And there are so many types of different signals. Not all of them are not all of them are the same. So you have to classify it first to what normal distribution fits it best, and then apply that. So we have a bunch of algorithms there. We have a second level learning that learns to differentiate between anomaly patterns. So that's another set of algorithm and models. The fourth step, we actually learn the relationships between all these different signals. And that is a set of different clustering algorithms that we use internally. And at the end, we do semi-supervised learning by taking feedback from our users, both implicit and explicit, and improving the models based on that. So we have a chain of a bunch of different algorithms, just to give you some statistics and the architecture of what we have. So you can gaze at the architecture, but I'll give you the statistics. So we process today over 3 billion samples a day, about 75 million different time series signals. This is from all our customers. Each one of these metrics has at least 2 models, one for the normal distribution, one for the abnormal. Sometimes it has 3 if it's in transition between the models. These models get updated with every sample that comes in. We have about 300 million correlation links that are updated daily, so we run the correlation algorithms every day. 7 million models that take into account different seasonal patterns that get updated every day. 30 types of learning algorithms, from classification to seasonality detection, trend, baselining, and they all have to interact to produce the result to our customers, which is find anomalies on their side. So there is a chain of algorithms, and we have to monitor all of them. It's not just one algorithm that we keep track of its performance. We have to track all of them and make sure they work in concert to produce the right result. So that's not very simple. And the architecture is complex. I mean, we use a lot of open sources. If anybody's interested afterwards, I can describe it in more detail. So how do we track the performance of our algorithms? We track them with metrics, as I mentioned. And this is an example of an anomaly we had recently, where we deployed something wrong in some of the algorithms, and it affected all of them. So we had an increase in the distribution, a change in the distribution of seasons detected for all the metrics. We had a lot of model switching that happened accidentally between different models that we have. So our classifier wasn't working well. Our anomaly quality scores also changed, and you can see it in the drop there. So basically, this anomaly was a result of a deployment. And of course, I could graph them in dashboards and track them manually, but I don't want to do that because I have an anomaly detection system, so why not let it do the job? So, of course, we set up our means to get a lot of anomaly alerts. These are some additional examples. So this is an alert we got, and this is an email alert from my inbox showing that there is an abnormal increase in the number of high-score anomalies and high-score anomaly metrics. And when we get and when I see this, I don't know these numbers. I couldn't even think about how to set a static threshold for that. When I see this jump of an increase, I know there must be something wrong. Either customers really sent us different data that caused this, or something went wrong with the algorithm. And in this case, we actually realized that we need a new type of model, and we developed a new type of model. So it will take into account this new behavior that one of the customers actually sent to us. Another example, this is an anomaly with multiple metrics. These metrics represent the distribution of seasonality detection algorithms in our system. Actually, this was a good anomaly. You can see it more or less May 24th, 25th, we deployed a new type of an improvement to our seasonality detection algorithm. And it actually, we saw the distribution change as we expected to provide better results in seasonality detection. So we expected this anomaly, and when we got it, we were very happy. But the point is, we didn't have to actually track it with any dashboard. We could just look at our, wait for the email alert and know that it happened. So to summarize, anomaly detection, this fifth step is really a mean to start closing the loop of the machine learning process. So to track and monitor anomaly detection can help you. It's not the final step, it's the first step. The first step is to really take these anomalies and actually help the machines improve themselves automatically, which is probably something you would need when you have mission-critical applications where you don't have the luxury of getting alerts about anomalies and fixing them kind of in the lab. So for example, autonomic cars would probably require an additional step after anomalies to actually start fixing and identifying new objects. So with that, I will conclude. Thank you. I'll take any questions.
Thank you very much. We have plenty of time for questions. We have 15 minutes, I think. So please fire away.
So you all get coffee.
There was a step on one of your slides called something like behavioral topology learning, right, which you glossed over quite quickly.
Oh, yeah.
Can you talk a little bit more about what that involves?
Sure. So, yeah, I didn't want to use this talk as a self-promotion, complete self-promotion to our algorithms. So what do we do here? Our approach has been a bottoms-up approach to doing anomaly detection. So we will first take each signal and learn that by itself, do the abnormal learning, and then try to combine the anomalous metrics by knowing who is related to whom. So here we actually use three types of algorithms. One is looking at the correlations in normal time. Here we are using a variation of neural network deep learning algorithms. So it's not linear correlations, but basically using stacked autoencoders, you can take in the signals. The output is a bunch of alphabet, and on that you do actually similarity between pairs of metrics. So that's one algorithm. Another algorithm is looking at their correlations when they are abnormal. So whenever there are anomalous metrics, so let's say I'm measuring an entire system. When something goes wrong, there are a lot of different signals that go wrong at the same time, and they become anomalous. So by looking whether they're correlated, they cluster together during these abnormal times rather than their behavior during normal time, actually gives us a very strong hint of whether they're related or not. So that actually is one of the strongest hints that we have today. It's even stronger than the normal patterns. So a lot of times they look completely different during normal times. If you look at memory and CPU, for example, even from the same machine, it might look completely different, but when something goes wrong with the machine, they will be anomalous regardless. That's an analogy. And the third one is using metadata that we get from the signals themselves. Usually the signals are not just sent as numbers, but with some metadata around them, and then we do clustering around that to know whether they're related or not. So at the end, we get this large graph with a lot of links between the metrics, and that provides an input to our anomaly detection system. Yes?
You showed what looked like an email that you received once an anomaly was detected. And it seems like this provides at the bottom there a way to give feedback on false positives. How do you handle the detection of false negatives for quality control purposes?
Right. So we haven't figured that out yet. I mean, we get them, but we get them directly from the customer that says, oh, there was something and you didn't catch it. That doesn't happen a lot because often they don't, I mean, even if we didn't catch it, they don't know. Because they didn't know before. And they're more sensitive to false positives than to false negatives, unless it's a really critical issue that we missed. So that happens less. So in those cases, we actually go and do deep investigations ourselves and try to figure out, why our models didn't pick it up. And sometimes we have to change the models. So we haven't found a way to automate the false negatives. This is really for the false positives and various types of false positives, and also reinforces the true positives, which is also important. Yes.
My question is very related to the previous one. How do you integrate the user feedback back to your models?
Right. So the way we take the user feedback today, let me go back to. So we have this notion of abnormal behavioral learning, which I glossed over really quickly as well. So that part is actually builds a model that ranks different anomalies and gives them a probability score based on how they look compared to all other patterns of anomalies that we've saw before. And when we get the user feedback, we actually start changing those scores. So and this is the way we do it today. We have ideas of how we can integrate into other parts of the system. This is the first point we tackled because it seemed to be the most relevant. So if a user says this is not interesting, it means this anomaly pattern is not interesting for a set of metrics that are related to each other, and we start reducing the score. Instead of mathematics, so not interesting could be, well, because, let me give you an example. If the number of visitors jumped from 20 to 100, and it's usually 20, let's say it's 20 for a month, and it jumped to 100, and they mark it as not interesting. Mathematically speaking, this looks like a very, very big anomaly, because it went from 20 to 100, 5 times, 500% increase. But then you ask them and they say, well, but this is Zimbabwe and 20 to 100 visitors is nothing compared to another country like the UK or Germany where usually I have 20,000 a day. So I don't care to get this anomaly. So it's not that mathematically it's wrong. It's a false positive contextually rather than mathematically. And then that score lets us actually give it a lower weight, so next time he might not get it compared to other anomalies. And the same for whether something is interesting or not. Something is interesting. So maybe if the number of visitors jumped from 20,000 to 20,000, 22,000, it might be very interesting anomaly for that person, not because mathematically it's more interesting than others, because contextually and from business side it is more interesting.
We have time for more questions.
So if anybody's interested in more details about the anomaly detection part, I'll be happy to provide it later. Anything about our architecture or algorithms, I'll be around.
We do have one more question.
So you use neural networks, and what type of learning algorithms you use in your neural networks?
We're using stacked autoencoders, so these are not supervised algorithms.
What else?
That's it.
That's it.
Yeah.
Okay. So no type of genetic algorithms or something like that.
Not for this component. We don't use genetic algorithms anywhere right now in our.
And how do you handle the question of topology of your neural networks?
Brute force.
Brute force.
Brute force. We have enough data, so we just brute force the heck out of it.
Well, if we don't have any more questions, let's thank our speaker Ira once again.
Thank you.
And you have just got yourself 5 minutes extra pause in the sunshine.
Yep.